Okay, let's start, guys. So in the previous lecture, we learned about the basic logic gates. We learned about the make of the transistor and how we use the transistor as a switch to create zeros and ones. We went through basic logic gates, including AND gate, OR gate, and inverter. We also learned about NAND gates and NOR gate. These two gates are referred as universal gates. We also learned about a technique called DeMorgan's, which we are going to explore today. Basically, we can turn any gate like AND gate into an OR gate by using bubble-to-bubble logic. And then we also looked at some of the application of the basic logic gates. Today we are going to explore what we learned in the previous lecture, and we're going to learn two new things. One is the truth table. We know that truth table is a form that form of the binary numbers that tells you about the functionality of your project. So it's a way of organizing information to list out all the possible scenarios. So for example, if you have two variables A and B, meaning 2 bits, there are 4 possible combinations which will go from 0 to 3. We'll also learn about the laws of the Boolean Algebra laws and rules and DeMorgan's theorem. Remember, as a designer or as a programmer, our goal is to cut down the number of wires, cut down the number of gates without compromising on the functionality of the project. And the idea behind is to minimize the delay, reduce the size of your device, and also the speed, increase the speed. So we're going to start off with the truth table, very basic that we did yesterday. So how the symbol looks like for the AND gate. For the OR gate, the NOT gate was basically a triangle with a bubble at the end. And then we had the NAND gate, which was basically an opposite of AND gate, so you had a bubble here. And NOR gate was the opposite of OR gate. Exclusive OR gate. Okay, all right. What was the Boolean expression for AND gate? Anybody remember? You got inputs A and B. It was A dot B, right? This is how you would write. So dot operator is basically AND gate. What about the OR gate? What is the Boolean expression for OR gate? Come on, guys, we need participation here. Yes, A plus B. Awesome. Alright, so not A you can write down as A bar, or you can also write down as A like this. Okay, so A complement or A bar, same thing. Similarly for B bar, B complement or B bar. What about the NAND gate? How would you, what's the Boolean expression for the NAND gate? Yes. Yeah. Okay, all right. So I'll write down as A dot B and then bar on the whole thing. Okay, all right. So NOR is an opposite of OR. So OR is A plus B. And then because it's an opposite of OR, so I'll bar on the whole thing. Okay. And exclusive OR is written as A, and then you have this plus sign enclosed in a circle, B. So this represents A exclusive ORing with B. Also, let's go ahead and also do the Verilog expression for these gates. How would you write a Verilog expression for AND gate with inputs A and B? Remember? So it will be A, and then we use the AND operator B. Correct? What was the Verilog expression for OR gate with inputs A and B? A, this vertical line, and B, correct? So A, not A would be this tilde sign with A, not B will look like this. NAND gate would be A ending with B, and then you have this tilde sign right here. A ORing with B, and because it's a NOR, so you got this tilde sign right here. And then A exclusive ORing with B is written as A hat B. Okay, all right. We will quickly go ahead and finish the truth table for each of these gates. What was the logic for the AND gate, right? When both inputs are high, the output is going to be high, and for rest of the other combination, the output is going to be 0. For OR gate, any of the input is high, the output is going to be high. Not A. What would be the output for the not A here? Come on, yes. Yeah, so A is 0, 0, 1, 1, so the opposite of that would be 1, 1, 0, 0. Yeah. Not B would be 1, 0, 1, 0. Okay. NAND is an opposite of AND gate, so if you look at the truth table for the AND gate, just take a complement of that. So 1, 1, 0. And because NOR is an opposite of OR gate, so look at the truth table for the OR gate and take a complement of that. Exclusive OR gate. Does anyone know what exclusive OR gate? What is the property of the exclusive OR gate? Yes. Yeah. Yeah, when there's only one high, or if the number of ones is in odd. Okay. So 1 is considered as odd, so this is going to be 1. This is also going to be 1, and this is 0. Okay. All right. Moving on to the truth table for the laws of the Boolean. This was proposed by George Boole right here. Okay, so it is a set of the rules used to simplify the logic expression without changing its functionality. So if you look at the first one, the Boolean expression a plus 1 equals to 1, so it's kind of a, because we know that plus represents an OR gate, so in other words, if I try to make a circuit out of it, it would look something like this. One of the input is A, and one of the input is 1, right? And we know any of the input is 1 in going into the OR gate, the output is always going to be 1, right? And so this is a graphic form of this, what it is over here. A plus 1 is always going to be 1. And if you think of it, you know, in the third column where I have this equivalent switching circuit, this is 1 and this is A right here. If you provide a voltage here and you got a LED or a light bulb connected, it's going to lit up because there is a path for the electrons to flow. We call this annulment law or rule. Similarly, A plus 0 is going to be A, which means, again, plus would mean an OR gate here. This is A and this is 0. Because one of the input is 0, so the output is dependent upon A. If A is 0, it's going to be 0. If A is 1, the output is going to be 1. Similarly, if you move down, A dot we know is an AND operator. Okay. So one of the input is high, so output is really dependent upon A. If A is going to be high, meaning the output is going to be high. And that's what it reflects over here as well. This is how you would put it in a switching circuit. This rule is identified as an identity rule. I'll just do one more here. Okay, this is AND operator dot. So one of the input is A, the other input is 0. If any of the input going into the AND is 0, the output is going to be 0. Okay, so this is the sheet that you want to keep it with you for the rest of the term. You will need that. Let's look at some of the other rules and properties of Boolean algebra. Again, here you got A plus A bar. Okay, this bubble represents the complement A bar. This is A. Okay, so this is always going to be 1. And the reason for that is if A is 0, A bar is going to be 1. Okay, so this is always going to be a complement of each other. So the output will always be 1. And similarly over here,
dot is an AND operator. Okay, if you have A here and this bubble represents the A complement, because the two inputs are going to be complement of each other, the output is always going to be 0, and we call that complement rule. Similarly, A plus B equals to B plus A. This is a commutative property, and here is the DeMorgan's theorem, which is going to be very, very important one. I'll talk more about it in my in the next example that we would do. Actually, in one of the examples that we would do. There are some other algebraic laws of Boolean that were not included in the table. I'm just gonna skip these because these are very basic, and I'm sure you have done it many times in the past. So let's move on to our first example for the day. We have apply Boolean algebra laws and rules to simplify the expression. Okay, all right, so we have our left hand side here, and this is our right hand side. You guys can hear me at the back, right? Yeah. Okay. So I'm going to treat the left hand side, and hopefully I can make it equivalent to the right hand side. How can I get started here? Let me rewrite the left hand side here. X plus y dot x plus z. Okay, all right. You have to go step by step, not you. I want to answer from different individual every time. Come on. How can I get started? Can we just start like apply distributive law, basically opening the brackets, multiplying, right? Okay, so x times x is going to give me xx plus xz plus xy plus yz, right? So I just applied distributive law here. Okay. What is x dot x? What is x dot x? Yes. X. If you look at a dot a equals a, that's a idempotent AND law. So x dot x is going to be x plus, I'm just going to keep everything else same. Okay, all right. I can take x common here between these two terms, and then I would be left with 1 plus z plus xy plus yz. Okay, again I'm applying this distributive law here. What is 1 plus z here now? What is 1 plus z here, guys? If you look at the Boolean laws and rule, a plus 1 is always going to be equal to 1. We are applying annulment rule here. So x, and this is going to be 1, plus xy plus yz okay. If I take x common here again between these two terms, so I get 1 plus y plus yz, right? And then we know 1 plus y is going to be 1, so this comes out as x plus yz, right? And this is what we were aiming for. This is equivalent to the right hand side. So when I give you something like this on a homework or an exam, make sure you do this step by step and tell me like what, you know, rules and laws you have done. Don't just jump to the answer. I want to see the work process. I want to see the flow, how you have gone through. Okay. Is everyone clear on this part, what we have done? Okay. Okay. I want to move to the truth table for this expression right here. And I want to verify that this term on the left is equivalent to the one on the right hand side, and it gives us the same output. Okay, here's the expression again. This is the left hand side, this is the right hand side. At some point you will master it and you would not need to split it down, the expression, cut it down into small segments and then create a truth table of it. But for the first time when we are doing it, I just went ahead and break it down, so it's a little more easier to come up with a truth table. So if you look at the left hand side, I've split it into two parts, x plus y, x plus z. Okay, we are going to perform OR logic in those two, and then once we have these two columns ready, we can apply AND logic onto it. So moving on to the x plus y. Any of the input is high, the output is high. We are looking at these columns right here, x and y. 0, 0 is 0. 0, 0 is going to be 0. 0, 1 is going to be 1. 0, 1 is going to be 1. 1, 0 is going to be 1. 1, 0 is going to be 1. And 1, 1, these two are also going to be 1. X plus z. Now we are looking at this right here and this right here. X plus 0, 0 gets you 0. 0, 1 gets you 1. 0, 0, 0. 0, 1 gets you 1. 1, 0 is 1. 1, 1, 1. And these two are also 1. Okay. All right. Now moving on to the x plus y ending with x plus z, meaning you are looking at these two columns. And this time you are going to apply AND logic. And AND logic is when both the inputs are high, the output is going to be high. 0, 0 gives you 0. 0, 1 gets you 0. This is also 0. And for the rest of the combinations, it's going to be 1. Okay. So this is the left hand side. I'm going to move down to the right hand side of the equation, and again I have split it into x and y plus y dot z. X is basically this column right here, so I'll just rewrite it. 4 zeros and 4 ones. Y, z. So we are going to perform AND logic here because it's a dot here, y dot z, so it's an AND logic. 0, 0 gets you 0. 0, 1 gets you 0. 1, 0 gets you 0. 1, 1 gets you 1. 0, 0 gets you 0. 0, 1 gets you 0. 1, 0 gets you 0. And 1, 1 gets you 1. And then x plus yz, which is basically this and this. And we are going to perform OR logic here, right? Any of the input high, output is going to be high. 0, 0, 0. 1, 1, 1. 1 and 1. So if you notice here, your left hand side is actually equal to your right hand side. Okay. Let me ask you a question. If you go with the left hand side, if you want to design your circuit using the equation on the left hand side, how many gates you would need? Yes. Is that right? And if you go on the right one, how many gates you would need?
2, right? So in the left hand side you would need 2 ORs to make this, and then 1 AND gate to connect these two, right? And in the right hand side equation you need 1 AND, and then you need 1 OR to connect these two, right? That's what our next goal is, to design a logic circuit using these equations. So moving on to the next page. Okay, this is where this is going to come in handy here. Okay, I'm going to work on the left hand side. So I need 2 OR gates. Now we need 1 AND gate. Okay, so this is going to be my X right here. This is going to be my Y. This is going to be my X here again, and this is going to be my Z. Okay, we know that this is a OR gate. This is my AND gate. You know, when you are trying to go over a wire, you use this thing right here. So this is X, okay, and this right here is my this is the left hand side, sorry, left hand side. Okay, so we're not going to create a Verilog code for it, but I want to show you something here. We'll do coding in our next few lectures. So anything that's in blue are basically your inputs here, right? Inputs, and they could be declared as wires, but you don't necessarily have to. All the wires that you see in black, those are wires. A wire is something that connects the output of a gate to an input of the another gate. Okay, and anything that you see in green is basically your output. So this should really help you to come up with a Verilog code, because you know what are your inputs. Your inputs are in blue, which are going to be X, Y, and Z. You know your output is going to be LHS, and the wires are going to be these right here, that coming out of the 2 OR gates. Okay, let's create a digital logic circuit. We actually refer this to as combinational logic circuit or diagram. Okay, right, let's move on to the right hand side. I need an AND gate.
Okay, and I also need a OR gate. So this is going to be my Y, Z, and this is going to be X. Okay. And this is going to be my output, which is the right hand side of the equation. This is the AND gate, and this is the OR gate. Okay, let's verify some logic here. Say I got X set to 0, Y is 1, and Z is 1. Okay, so X is 0, Y is 1. That would mean you get 0 and 1 here. 0 and 1 goes into OR gate. What do you get here? You get 1 here. Again, you get 0 here and 1 here. 0, 1 goes into OR gate. You get what? 1. 1 and 1 goes into AND gate. The output will be 1. Okay. Similarly, we'll do it over here. Y was 1. Same logic. X is 0 and Z is 1. 1 and 1 goes into AND gate. You get what? 1. X is 0. 0 and 1 makes a. So you basically got the same answer using both the circuits. But we preferred this because we want to save on number of gates. Also, if you look back to the truth table, I basically applied 0, 1, 1. X was 0, Y was 1, Z was 1. So 0, 1, 1 also gave me 1 here. And for the right hand side also 1. So we've been able to verify the logic using the circuit diagram plus also the equation and the truth table. Shall we move to the next example? Is everybody following me? Okay, all right. Sweet. Okay, example number 2. For the logic circuit diagram below, simplify the equation X. Now we are reversing the process, and we have a digital logic diagram, a circuit. We are going to derive an equation out of it first, and then we are going to simplify it using DeMorgan's or Boolean Algebra. So if I ask you what is going to be the Boolean expression at the end of the at the output of this OR gate right here? Yes, guys. What is going to be the output here? You got A going in here and you got B going in here. So this is the output here is going to be, what is the Boolean expression? A plus B. Thank you. Okay. This is B right here. So this would be what? B bar, correct? B bar and A plus B going into AND gate. What is going to be the expression here? A plus B dot B bar, correct? Right? Okay, awesome. Again, we have B here. You can put in the parentheses if you like. Okay, you got B here and you got C here. B and C going into an AND gate, the Boolean expression is going to be B dot C. Okay. And then you got B dot C and this going into OR gate. So X is going to be what here? A plus B dot B bar and then plus sign B C. Okay. All right. I'm going to apply distributive law here and open the brackets. So this will be A dot B bar plus B dot B bar plus BC. Okay. what is B dot B bar here? Say it again. 0, right? So A dot A bar is 0. So this would mean this term is going to be 0, and this is the complement. So you get A dot B bar plus BC. Can you further simplify this equation? Yes, guys. Can you further simplify this equation? A dot B bar plus BC. We really cannot, right? So this is where we stop. Okay. And if you have to make this circuit, you basically need 2 AND gates. And then you need 1 OR gate. This will be my A. Now B bar, you can do it 2 ways. Either you can have a bubble or you can do an inverter. During class I just prefer bubble because it's just easier, right? So this would mean B bar, okay? So you get A here and you get B bar here. And then this is going to be B and C. So this is B, this is C, again this is AND gate, this is OR gate, and your output right here. Okay. So we had how many gates? 1, 2, 3, 4, 5. Now we have 1, 2, 3, and if you consider this 4, we have 4 gates now. Okay. Usually we use these Boolean algebra rules and laws in when we have number of variables less 2 or 3. We will be doing circuits where you would have more number of variables, and therefore the K-map, which is another technique that we would learn, we use that technique to simplify the expression. But this is a good start with the Boolean algebra rules and laws, but it's not, the K-map is more effective than this. Right, moving to our next topic, which is apply DeMorgan's theorem, simplifying the expression. If you remember, we learned about bubble to bubble logic in the previous lecture, where you would change an AND gate to OR gate by adding the bubbles where they were not, and then removing the bubbles where they were. Okay. So say you had this A dot B bar on the whole thing is equivalent to this circuit right here. Correct? A dot B ending and then bar on the whole thing, so you got this bubble. Is that equation and this circuit is equivalent? It is, right? Okay. Now, if I have to use the bubble to bubble logic to convert this AND gate to OR gate, what do? I change the AND gate to OR gate. You have a bubble here. I remove the bubble here. There's no bubble at the input, so I add bubbles. Is this equation right here is equivalent to this circuit right here? It is, right? A bar plus B bar, if this is your A and this is your B, right? And similarly, if this is A and this is B. Similarly, over here, using that bubble to bubble logic, we have A and B ORing, and then the bar on the whole thing, so we need a bubble here. Okay, this is A, this is B, correct? This is equivalent to Again, changing the OR gate to AND gate. There's a bubble, so we remove it. There's no bubble here, so we add bubbles here. DeMorgan's theorem can allow us to simplify the expression using these expressions, and we'll see, we'll do a couple of examples and you'll see that. Okay. Say you have three variables, A, B, and C. Again, we are going to come up with the expression here. What is going to be the expression here, guys, at the output of this NAND gate? So this is a NAND gate, and this is all right. Who was it? Yeah. So B dot C, and you said bar,
and it's going to be on the whole thing, right?
Correct. Okay. And what about the expression over here now?
What would that be? Jeremy?
What is going to be the expression here? Plus. Correct. And the bar on the whole thing, right? Don't forget that. It's bar on the whole thing because there's a bubble right here. Okay. Say this was F. Okay. So I'll just rewrite the equation here. F equals to A plus, and then we have this bar on the whole thing. Okay. And also let me rewrite the DeMorgan's law here, which says A plus B bar on the whole thing is equivalent to A bar dot B bar. Okay.
When you have a bar on the whole thing, you can actually break it using DeMorgan's law. And again, I like to do it, make it simple and easier for students, so I break it down again. You can think of it as this is, say this is your X, okay, and say this is your Y, right? So I can technically write this equation as X plus Y and then bar on the whole thing, correct? Yes. So, and we know A plus B bar on the whole thing is equivalent to A bar dot B bar. Can I transform this equation into this, right? Okay. What is A here? A is X and B is Y, right? And what is X here? A, right? Okay. And then I got a bar on the whole thing dot B. B is actually Y here, and Y is equals to B bar, B dot C bar, and then bar on the whole thing, right? Correct? Is everybody following this? How did I come from here to here, right? Let me just go back and do it again. I'm actually renaming my variable just to make it easy. I'll say this is my X and this whole thing is my Y. So I can technically write it down as X plus Y and bar on the whole thing. I'm going to transform this equation into something like this using DeMorgan's law, which is going to be A bar dot B bar, which is equivalent to my X and Y. And X was A, so I put A as here, bar here, this bar goes here. Dot Y, Y is B bar C, so I type B dot C bar on the whole thing, and then this bar goes here. When you have two bars on a variable, what do you do with that? Yes. Yeah, they just cancel out, right? They just cancel out, and it's also one of the properties. See if I can. Right, it's not included in here, but it's also one of the property. If you have bars on two bars on the whole thing, you can cancel them out. So this comes out as A bar dot BC. Okay, so in other words, this circuit
could be transformed into something like this. So A, B, C, and then A is going to be the bubble here because he got A bar, B, C, and then this is going to be F here, right? Okay, right. So you had one NOR gate and one NAND gate. Well, you can actually just make it with an AND gate and an inverter, okay, which in some cases may be more convenient. Does everybody understand how we use DeMorgan's law here? There's one more example, which is the last example. Okay, we are going to do the same thing. What is going to be, this is the AND gate here, NOR gate here, NAND and NOR. Okay, all right. What is going to be the expression at the output of the AND gate here? BC. Okay. What is the expression here at the output of the inverter? B bar, right? And this is A here. So what is going to be the expression at the output of this NAND gate right here? Come on. A dot B bar and then bar on the whole thing, correct? Because we got a bubble here. What about the output at the NOR gate? You got A, this is A, plus BC, and then output bar on the whole thing, and Q, because I don't have much space over there, so I'm going to just write it over here. Q is going to be A plus BC plus A dot B bar, bar on the whole thing, and then I'm going to have bar on this whole thing because I got this bubble right here, correct? Okay. All right, again I'm just going to break it. I'll just say this part say this is A and say this is B. Okay, so I can basically write it down as A plus B bar on the whole thing, which is equivalent to what? A bar dot B bar, A bar dot B bar, correct? Okay, now I'm going to restore values for A and B. In above equation, okay. All right, what was A here? A plus BC bar on the whole thing plus you got bar here, so this goes here, dot, so you got dot here, and then you got B. B is A dot B bar and bar on the whole thing, and then you have bar here, so you get this bar right here. What are we going to do with these two bars here? Cancel out, right? Okay, so these could be written as A plus BC A dot B bar, right? I can just apply distributive law here and open these brackets, so I get A dot B bar plus B dot B bar dot C. Okay, what else I can do here? What is A dot A? Yes, Hunter? A dot A 0. So you got A dot A.
if A is 0, that will mean output will be 0. So it will be 1. A, right? It will be A.
Okay, so this here, A dot A is going to be A. Just keep B bar as it is. What is going to happen to this B dot B bar? That is 0, right? So basically, here you are doing the, what was the A dot A rule? Idempotent. And B dot B bar was what? Complement. Okay, so notice here, this complex equation is actually equivalent to A dot B bar, which is what basically it's AND gate and inverter. This is your A and this is your B with the bubble here because this is B bar, right?
This is actually going to be on your pre-lab as well. Yes. Right.
Right?
Okay, awesome. Thank you. I think we are going to finish today's lecture here. Okay. I'll see you guys in the lab.